So we're moving on to section 2.7. This is inverse functions. So this is our last bit in chapter 2. So after this, we'll start going into special kinds of functions. So we're going to talk about inverse functions. So inverse functions are simply two functions that undo each other. We're going to see that here in a second. But inverse functions undo each other. And what I mean by that is that they're going to undo the operations that they are performing. So they're going to reverse those operations. They have to reverse them in the correct order, though. So if we have functions f and g are two functions such that f composes g equals x for every x in the domain of g, and g composed with f equals x for every x in the domain of f. So essentially the part we're really going to worry about is, can we do this? So if we have two functions f of x and the composition of f and g is x and the composition of g with f is x, then the function g is an inverse of the function f and is denoted with this f in the superscript of a -1. So this -1 is not supposed to be like a, it's not a power. What it is a designation to say that we have f inverse. So it just does a little note. This means inverse of f, not reciprocal. Occasionally I'll see somebody come up with that and then they try to give me a reciprocal function. That's not what it is saying. Thus, f composed with f inverse equals x and f inverse composed with f equals x. The domain of f is equal to the range of f inverse and vice versa. So what we have here is that we have a function f, and then we had g of x, which, if this is true, we can say that g of x is just this f inverse. And technically, I can say that f is also just g inverse, but we're going to do this just one way for right now. So the domain of f is going to turn into the range of f inverse. The range of f becomes the domain of f inverse. So that's what this part is talking about. The domain of f is equal to the range of f inverse. So this is a property of inverse functions, is that what they're doing is they're swapping their domain and range. So inverse functions swap domain and range. So we're going to go back over that a little bit more. First, we're just going to show if two functions are inverses of each other. So we have these two functions. We have f is 4x minus 7 and g is x plus 7 over 4. So if you remember, I said that inverse functions undo each other. So notice here that this one has a multiplication of a 4 and a subtraction of 7. But over here, I have a plus 7 and a division by 4. So if they go in these operations in the correct order, these functions should undo each other. So don't always look at two functions and go, oh, the operators flipped. They must be inverses, because that's not always true. We still have to test it. So we need to see if f composed with g is going to equal x, and if g composed with f also will equal x. So f composed with g, so f is 4x minus 7, so we got 4. And then remember, this is saying that my x is replaced with g of x. So I got 4 times g of x equals 7. Well, we know that g of x is right here is x plus 7 divided by 4. And then we have our minus 7. So right here we see that we're dividing by 4 here in g, but f has its multiplication, and those are going to cancel out. So then that x plus 7 is free now. And we have the x plus 7 minus 7. So we got plus 7 minus 7, so both cancel out, and I'm just left with x. So as we see, the inverse functions are undoing each other. Now we got to make sure this happens the other way around. So we have g composed of f. So we got g on the outside, so x plus 7 over 4. We know we replace our x with f of x. So it's f of x plus 7 over 4. And we know f of x is just x, 4x minus 7. So we got 4x minus 7 plus 7 over 4. So we're going to do our operations again. It's just we're doing them in a different order because we're going to have this minus 7, this plus 7 are going to cancel, leaving me with 4x over 4. My x's cancel, leaving me with just x. So yes, f of x and g of x are inverses of each other. So I can go back here and just say, well, I don't have f of x and g of x. I have f of x and f inverse. And I can only say this part here if I do in fact know that g is an inverse. Okay, so for your worksheet number 1, work on this problem here. So you're going to see their inverses again. So we have f of x is x minus 6 over 2, and g of x is 2 times x plus 3. So we're going to do the compositions of these functions. Remember, you have to do both compositions and make sure they equal x to determine if they really are inverses. Okay, so like I said, we have to do these compositions. So we have f composed as g, and f is x minus 6 over 2. So we got g on the inside, so now it's going to be g of x minus 6 divided by 2. And we know that g of x is just going to be 2 times x plus 3. That's my g minus 6 divided by 2. So we can't do anything directly as is. Well, actually, there's one thing we can do. So we can divide by the 2. So I'm going to do it like this. So we can break up because we have a summation here. I can do this divided by 2, and I can do this divided by 2. So just break up the difference over the denominator. So we're going to end up with x plus 3, and then 6 divided by 2, so minus 3. So it may not have been obvious right away that these were inverses. That's why I said you always want to check, because sometimes you can't always see that we have all the operators reversed here. Now, if I go back and do it the other way, we have g of x is going to be my outside function, so that's going to be 2, and x is going to replace with f of x, so 2 times f of x plus 3. We know that f of x is just going to be x minus 6 over 2 plus 3. So now we replace f with x minus 6 over 2. So we'll start simplifying. We'll distribute this 2. And once we do that, we're going to get 2 here, 2 here. They cancel, leaving me with x minus 6. And 2 times 3 is going to be plus 6. So once again, we're going to be left with just x. So yes, they are inverses of each other. So as a reminder, that means that f is an inverse of g and g is an inverse of f. So they inverse each other. So both of them are technically inverses. All right, so going back to this problem here, just for a little demo. So one of the things we talked about is the switching of the domain and range. So if we look at f, Let's say we put in 2. F of 2 is going to be 4 times 2 minus 7, or 8 minus 7, which is equal to 1. So what we have here is 2 is in the domain, because I input it and I get an output. 1 is in the range. And let's just make a point here. This is just of F. Well, let's say we go back and we look at G. So remember, G has an inverse, so that domain and range should switch. So this one, that was an output here, we're going to put in here. So we're going to take a number from the range and put it into G. So once I do that, we're going to end up with 1 plus 7 over 4, or 8 divided by 4, which is 2. So what we see here is that 2 outputs. So here, 1 is in the domain of F, and 2 is in, oh, sorry, not F, G, and 2 is in the range of G. So what we have here, like I said, domain and range switches. So that means everything that is a output of F would be an input of G to get the same kind of ordered pairs. So here we got an ordered pair that is 2, 1, but that ordered pair flips here to 1, 2. So essentially we have X, Y, and what happens is X, Y switches places when we look at the inverse function. So it's that switching of your X and your Y, or your inputs, your outputs, or your domain and range is what we're going to use to find inverse functions. So how do we find an inverse function? The equation for the inverse of a function f can be found as follows. We're going to replace f of x with y in the equation for f of x. So let's say we had, my function was f of x was equal to 2x minus 1. Then what we're going to have here is we're just going to write y equals 3x minus 1. So we have a reason for that. So remember, we're looking for the inverse function. So first we're going to exchange x and y. So this is f of x, and technically, assuming this is a function, which it is, this here is actually your inverse function. We're going to put y in there. No, wait, sorry. Fix that again. Yes, so that would be your inverse function. So we don't usually like our inverse functions like this. So the next part is we're going to solve for y. If this equation does not define y as a function of f, then the function of f does not have an inverse function, and this procedure will end. If this equation does define y as a function of f, then the function f has an inverse function. So like I said, I got ahead of myself here because I knew this is going to be an inverse function. Sometimes we do the switch, we don't actually get a function back. But what we're doing here is we just want to solve for y. So we take our x equals 3y minus 1. So we'll add x to both sides, or x to both sides. We'll add 1 to both sides. So we got x plus 1 equals 3y. And then if I divide by 3, I get x plus 1 divided by 3 equals y. So my last step is f is an inverse, if f is an inverse function, has an inverse function, then we're going to replace y with f inverse. So we will end up having f inverse of x is going to be equal to x plus 1 divided by 3. So we can verify our results once again by doing the composition just to make sure it works. So we are going to find the inverse of 2x, or fx equals 2x plus 7. So our first step is we're going to replace f of x with y. So we have y equals 2x plus 7. Our next step is we're going to switch our domain and range. or we're going to switch our x and y. So now we have x is equal to 2y plus 7. So this is where we get the inverse. So you can have inverses of any kind of equation. We're looking for inverse functions right now. So I'm just going to call that the inverse because I don't know if it's a function yet, technically. I mean, it's going to be a function. Next, we solve for y. So we'll subtract 7 from both sides. We got x minus 7 equals 2y. If we divide by 2, we get x minus 7 divided by 2. X minus 7 divided by 2 is going to equal y. And then my fourth step is that I'm going to replace y with f inverse. So f inverse is going to be equal to x minus 7 over 2. And then technically we're supposed to check. I won't check every single one, but we'll check this time. So I just want to make sure that f and composed with f inverse actually outputs this x. So f is going to be the 2, and then we have f inverse plus 7. So that is going to be 2 times x minus 7 divided by 2 plus 7, which is going to leave me with x minus 7 plus 7, which is going to give me x. So that works. Now if I do f inverse composed with f, most likely the same thing is going to happen. So f inverse is going to be the x minus 7 divided by 2. So we'll make that x replaced by f of x. So it's f of x minus 7 divided by 2. We know that f of x is just going to be 2x plus 7. So we get 2x plus 7 minus 7 divided by 2. It's going to leave me with 2x divided by 2, which is going to leave me with x. So it worked out. So that is the inverse function of 2x plus 7. Okay. Let's try another one. Oops, I accidentally went backslide. So here we have fx is going to be equal to the square root of x plus 5. So we're going to write y equals the square root of x plus 5. First step. Then we're going to switch the x and y to get my inverse. So x is equal to the square root of y plus 5. This may or may not be a function. So what we have here is we got the square root. So if we want to get rid of that, we have to square. So if we square both sides, we get x squared is going to be equal to y plus 5. So if we solve for y, we're going to put that y is going to be equal to x squared minus 5. So my inverse, and we're going to come back to this one here in a second. Is going to be x squared minus 5. So we got to be careful because this one technically doesn't have an inverse to it. But this is supposed to be the inverse function. But let's just do a check here quickly to make sure things work. So if I do f composed with f prime, then we're going to get the square root of f, not f prime, I'm sorry, f inverse squared minus 5, which is going to be the square root of x plus 5 squared minus 5, which is thus going to be the square root of I made a mistake somewhere. Let me go back a second. So we have f, okay, sorry, this wasn't squared yet. Go backwards. I switched my two functions. I do that. Let me do that one more time. So we're doing this. So we have this function here, f And then this is going inside. So we start here. I looked at that one and started doing that one. Then f prime is supposed, or not f prime, f inverse is going to be x squared minus 5 plus 5. That makes a lot more sense. And then we're going to get the square root of x squared because the 5's cancel, and the square root of x squared is just x. So like I said, we're going to come back to this one because I have to put domain restriction on it. But we're not quite to that yet. But since you have ones like this in your book, I wanted to go over it. So if we go the other way, then we start with the x squared. So that is going to be the fx on the inside, fx squared, which is what I accidentally tried to do earlier, minus the 5. So we know f is just going to be the square root of x plus 5. And that's going to be squared minus 5. Y square cancels the square root. That's x plus 5 minus 5 equals x. So it does work. I'm going to put a little note here. This works just as long as my x values stay over 0. So we're going to come back to why that's true. So this one here. So first step is we're just going to make it a y equals 3x squared minus 4. Then we switch our x and our y, so then we have x is equal to 3y squared minus 4. So you may remember that when we have a y squared, this is not a function. So this is an inverse, but not a function. Because if I try solving this, we're going to have x plus 4 is going to equal to 3y squared, which means then I'm going to get x plus 4 divided by 3 equals y squared. So if we solve for just y, I have to do a square root, which means I get a plus or minus square root of x plus 4 divided by 3. So that means I have two outputs for each input. So what's going to happen here is that what you'd see is that y, if I put in x, is going to be either the negative square root of x plus 4 over 3, or y would be equal to the positive square root of x plus 4 over 3. So we have no inverse function for fx, and I'm going to add a little note here, on its complete domain. So like I said, we are going to go back and revisit these two, but just want to show you that. So first two we found an inverse, so technically we'd say this one doesn't have an inverse for now. As long as we look at it on its complete domain, it doesn't. So your worksheet number 2, you have 3 problems here. So see if they have, and we'll look for their inverse and see if they actually do have an inverse. And then we'll come back and we'll check our answers. All right, so let's start with A. So we have g of x is equal to 2x minus 3 over 2. I'm not going to do the checking on these ones. I'm just going to find the inverses if they exist. But first step is we're going to change that to y equals 5x minus 3 over 2. We're going to switch the x and the y. So we get x is equal to 5y minus 3 over 2. So this is where we get the inverse, least inverse relationship. We just need to know if it's a function. So we start solving for y. So I got this 2 here. Let me do this, break it up a little bit. So I'm going to counteract this 2 by multiplying each sides by 2. So then I'm left with 2x equals 5y minus 3. Then I'm going to add the 3. And I have 2x plus 3 equals 5y. Then we're going to divide by the 5. So we get y is going to be equal to 2x plus 3 over 5. Or we can say the inverse function is going to be 2x plus 3 over 5. All right, so next will be b, which we'll do right here. So for b, we're looking at hx equals the cubed root of 2x minus 1. So this one, we're not going to be worried about not having inverses or weird inverses. So we just make that y equals the cube root of 2x minus 3. So then we just flip the domain and range. So we have x is equal to the cubed root of 2y minus 1. That's after we get this is our inverse. And then we just start solving for y. So to get rid of the cubed root, we're going to cube both sides. That's going to leave me with x cubed is going to be equal to 2y minus 1. Then we're going to add the 1 both sides, so we get x cubed plus 1 equals y. And then we get x cubed plus 1 divided by 2, 2y, is going to equal just y. So what we're going to get here is that h inverse is just going to be x cubed plus 1 divided by 2. All right, I think we probably already have a guess what's going to happen with C here. So we got those squares again. So hopefully you caught this part, or you may have stopped and said, hey, this doesn't have an inverse. But we're going to rewrite this as y equals x squared plus 3x, minus 4. So when we switch the domain and range, this becomes x, and then all my x's become y. So here we see that y squared. Forgetting that y squared, forget that's not going to be a function. So once again, we have no inverse function. On the domain, or the entire domain of Px. So here we're going to look at graphically if something has an inverse to it. So a function f has an inverse that is a function. And we're going to call your f inverse if there is no horizontal line that intersects the graph of the function of f at more than 1 point. So horizontal line test is testing if we have an inverse function. Vertical line test is what you test to see if if the function itself is the graph itself is a inverse. So vertical line test is looking for functions, and horizontal line test is looking for inverse functions. So these are both functions here. We got an absolute value function, and then we have a exponential function. We want to know which one of these actually represents a function. I don't know why this says C when that should be B. So this is my function here. So we see with this function that if x equals -1, then we are going to get y equals 1 as an output. If f equals 1, then we're going to get an output of 1 again. So what this means is that if I turn this around and I look at the inverse function, then this 1 has to go inside here, right? And what's going to come back out is that I had 2 x's that gave me that 1. So remember, these are your y's. So what's going to come back is that, well, there's 2 solutions to this. It's either -1 or 1. So we could do that again, looking at another point. So let's say we look at 2. Well, or -2. F at -2 is going to output 2, and f of +2 will also output 2. So x, y, x, y. And once again, what the inverse is going to do is it's going to put in that y, and we're looking for the x values that would have been outputted because our domain and range flips. And once again, we'd see we get -2 and 2. So what we see here is that f inverse would not be a function. Now, if we look at the other one, we look at B, we see here that, well, let's call this function a different name. We already used F, so this is going to be G. So let's say we looked at G of 1. Well, G of 1 is going to be 3. And that's the only thing that we're going to see there because there's not another value that's going to give me the 3 back. So we look at the inverse of it and we put 3 back in. The only thing that 3 can pop back out is that 1. So we call this a 1-to-1 function. But yeah, so this one's going to have an inverse. So G inverse would be a function. And I need to make a little change here because this is wouldn't say that use the inverse function. We'd say the inverse of fx would not be a function. The inverse of g of x would be a function here that we can call f prime. So this is what we talk about the horizontal line test. If I can draw a line horizontally and I hit more than once, that means that when I look at my inverse relationship anyway, that I'm going to have an input that's going to give me 2 outputs. So the graph of your f inverse is going to be a reflection of f about the line y equals x. So the line y equals x, if I go back here, oops, just a second, I'm gonna grab that again. I would be this line here. So this is going to be g of x, so this one we know has an inverse. Then what we'd see is that we'd have a reflection, like, do it like this. Sorry, I have a hard time with smooth lines with this. This would be your inverse function because it's going to be a reflection over this line y equals x. So looking at this a little bit more, so remember that when you're looking at inverse function, it's flipping domains and ranges. So we have a point here that has an x value of 1 and a y value of 2. And this function here is going to be f. So if I want to have f inverse, which I'm going to do in red, this point ends up turning into a point that is going to be right here at 2, 1. So your x and your y has switched places. This point over here that we have at -1, 0, x and y would switch and we would have a point at 0, -1. This point we have right here at -2, -2 would flip, and that means that I would also have a point here at -2, -2. Let me go grab my line tool. So this function would be your F inverse. And once again, if I draw that line of reflection, let's do it in green. We see that F and F inverse are just reflected over that line, y equals X. Sorry about that. Got a call, son. For your worksheet. So determine first to see if these pass the horizontal line test. Then if they do, graph the inverse of the function. We see here, we got this parabola here. This is not passing the horizontal line test. So we cross that, make that horizontal line, we cross twice. So the function does not have an inverse function. Here we see we cross there, and we only cross once. It doesn't matter what line I draw, I only cross once. So this function has an inverse function. Like I said, all relations will have an inverse. We're just determining if that inverse is going to be an inverse function because we're concerned about functions with algebra. All right, so that takes care of the first part. So next we have to do the graphing. Okay. Like I said, this one we're not concerned with. This one will have an inverse, but we'll say this is function f and we want its inverse. Well, let me make that in red. The red line is going to be f. Now, what would be helpful is just picking a few points here. So we got a point at 1, 2, 3. So 3, 0. And then we have this point here. Well, that one's at 5, 1, 2. So a couple points will help us. This one is at 10, and that's approximately 4. We'll just get as close as we can to it. So now when we do the inverse, we're just flipping those points. So instead of being 3, 0, we're going to look at 0, 3. That's going to be part of my inverse. Instead of having 5, 2, we have an inverse. It's going to give me 2, 5. Instead of having 10, 4, we're going to look at 4, 10 for the inverse. Graph that again. Let's try to do this by hand. It's not always that smooth. So we see that is right there, the inverse. So remember this whole thing about how we don't have an inverse on the domain of f? So we're going to talk about restricting domains. So if f does not have an inverse function on its domain, sometimes we can restrict the domain of f and find an inverse function on the restricted domain. So we saw this graph earlier. This was on last slide. So this one was said didn't have a function or didn't have an inverse function. So we have no inverse function on the domain of fx. However, I could restrict the domain. So we see that the problem here is like this half. If I keep that half, then I can't pass a horizontal line test. So if I remove everything from here to here, this part will have a inverse function. So here, my domain, it's hard to see here, but this is at -1 to infinity. So this is a restricted domain. So we have a restricted domain. It's just looking at the function from -1 to infinity. So this is only fx on -1 to infinity. In here, we would actually have an inverse function. What that is. Second. I cut off stuff, so there's a 10, 11. So I think that point goes here. And then this point up here would end up going to 1, 2. Trying to get the points in the right spot. Here, just a second. Maybe we can fix those points there. Sorry, I hit a point backwards. So it would look like this. It would be the inverse function. So we want to restrict the domain of fx equals 3x squared minus 4 such that it has an inverse function. Once we do that, then we're going to find the inverse of the find the inverse on that restricted domain. We're going to get a little practice for something else here in a second. So let's make a little graph of what this would look like. So we know this parent function is x squared. And it's x squared, it's going to be vertically stretched and shifted down 4. 1, 2, 3, 4. So it's going to be here. And it's going to be really skinny. And to make it perfect, we just need a rough sketch. So what I see here is that it doesn't pass the horizontal line test unless I just cut off this half of the function. So I would restrict the domain because what it looks like you can see that I cut it off at is at 0. So we're going to restrict domain to 0 to infinity, because 0 is okay. We only have 1 point there. So we look at 0, we include it to infinity. All right, so now we're going to find the inverse of the function on that domain. So here, not much is going to change. Just remember that what we're looking at is only half of the function. So we're going to look at y is going to be 3x squared minus 4. We're going to switch the domain and range. So we get that x is equal to 3y squared minus 4. So if we solve that for y, we're going to get x plus 4 equals 3y squared. If we divide by 3, I'm going to switch this to this way and keep going. We divide by 3, we get y squared is equal to x plus 4 over 3. And then y would be plus or minus the square root of x plus 4 over 3. So all we're going to do is that we restricted this, so we only need half of this. So do we have the positive half or the negative half? Well, because I cut off the negative half, what we see here is that what we're only keeping is this positive half of the function. So we're only keeping the part that's going to output or be the positive x values, meaning when we switch this, it should be like the positive y values. Because once we do the inverse of this, from what we graphed, we should get this. So we should only have the positive y values. So we're only looking at y equals absolute, or sorry, not the absolute value, but looking at positive root of x plus 4 over 3. So if we have fx is 3x squared minus 4 on the domain of 0 to infinity, the inverse is going to be the square root of x plus 4 over 3. So if we have something doesn't behave, doesn't give us a function as an inverse, we can do some things like restrict the domain to figure out what that inverse would look like. Now we do have an inverse function as long as we restrict that domain. So the last problem here, fx is x squared plus 3x minus 4. What you're going to do is you're going to try to, you can use a calculator if you need to, but see where the graph of this is and figure out where do I need to cut off half the graph and what is the domain that I'm going to keep. And then we're going to go back and do this, and I'm going to do it by hand because we're going to get prepared for something else in the future. Okay. So you could have factored this and at least get these two parts to graph it. But this part right here may not have been so obvious. So this is a point at negative 1.5 and negative 6.25. So what we see here is that through this point here, then I'm only going to keep half my function. So what I can restrict my domain to, remember, you're restricting domains, so restricting x values, restrict domain to, if I only want to keep this half of my function, I'm going to start at negative 1.5 to infinity. So essentially this part is going to disappear for us. Now we're going to find the inverse. Because now that I cut off half of my function, this is half does something with an inverse. So we're going to have y equals x squared plus 3x minus 4. So this is one I gave you earlier. Oops, not bringing back that yet. We switch x and y, we have x is equal to y squared plus 3y minus 4. Okay. Okay. So we see here, we're going to get stuck and we're like, well, what do we do? So we're going to bring back something just as a memory here. So remember that when we have this over here, what we have is we have a parabola that is shifted down by negative 6.25 and shifted to the left by negative 1.5. So if I take x, I shifted the x to the left, so that means I have to add 1.5 directly to the x to get that shift. So that's for my x squared. Then to shift down, I get that negative 6.25. So another way we can look at this is that it's not going to be fx is going to be, we'll write this here, that x squared plus 3x minus 4 is the same as saying that I have x plus 1.5 squared minus 6.25. So this is what we're going to call vertex form, which is what we're going to be getting into very soon. So just a little preview of that. So I can instead write y is equal to x plus 1.5 squared minus 6.25. Sorry, interruption. So now if I look at this, well, this is x is equal to, y plus 1.5 squared minus 6.25. So now in this form, if I just add on to that x, we're going to have x plus 6.25 equals y plus 1.25 squared. So we need a square root to get rid of that square. So we're going to have the square root. Remember, we're going to talk about plus or minus. We'll get back to that in a second. Plus 6.25 equals y plus 1.5. Now, because I'm only keeping this side, we know that the graph of that is going to look like if I do that inverse. We would get this. So we're only keeping positive values again. So we're really just looking at, we're just keeping the positive x plus 6.25 plus y equals 1.5. So then I just subtract that. I get y is equal to absolute value, or no, sorry, to the square root of x plus of 6.25 minus 1.5. I'm just trying to get my marker to work here. There. So if we have fx, which is equal to 2x plus 3x minus 4 on the interval from negative 1.2, negative 1.5 to infinity, the inverse function is going to be f inverse of x plus 6.25 minus 1.5. Okay, and then a little side note, go back to this one. So we said that our inverse function was going to be x squared minus 5. So because that's an inverse function, we also have to make a domain restriction because we want this to reverse back to this. So this would look like this function here centered shifted down to negative 5. But once again, if I only wanted to keep half of that, I'm going to have to restrict the domain. So my inverse is actually going to be x squared minus 5 on the domain of 0 to infinity.